Comes on you. Start off. Great. Let's start off with a question. Let's say we have two current carrying wires. This is I. This is also I. D comma 0 and minus D comma 0. So we have an observer who's moving on the x-axis. So plot the magnetic field on x-axis versus x coordinate. Do you guys remember this? We have done something like this in electrostatics. Plus Q and plus Q find the graphs. So here J cap is taken as positive direction. J cap is positive. Minus J cap is negative. So let me show you one. I'll ask you one more like this. So listen. So I'll just change the colors here. Let this thing be green and this thing be red. Now, how is the field due to this guy? Put your thumb inside, rotate it. So this field is down and this field is up on the left side. Agreed? Here the field will be same thing, down on the right side and up on the left side. Now, when you're at infinity, field is 0. As you get closer and closer to the wire, remember the field ka formula is B is equal to mu naught I by 2 pi r. Means if you get closer to the wire, the field will blow off to infinity. If you go away from the wire, field will decrease. So as you get closer and closer to the wire, the field will go to infinity. Once you cross this, the field will be on the infinity, but it is going downward. It will go from infinity, touch the center point. It's a null point. The fields will cancel. And then it will continue to go this way, and then it goes this way. Clear with the graph? You guys remember this? We have done this in electrostatics. So you draw the graph above positive axis if it is in the j cap direction. If it is minus j cap, then you draw it below the x-axis. All clear with this? Hope you remember this thing. Now, you guys try this. Can you draw if this is I and this is I downward? Let's say. I'll just mark this again green. So this field will be clockwise. This field will be anti-clockwise. Remember here, in this case, there's no null point. Hope you realized it. The fields at the center won't cancel out. This will go here. This will go till here. After this point, the red line will start dominating like this. This. Got this? So if you get too close to the wire, it will go to infinity. The only thing you need to see whether it is pointing up or pointing down. Pointing up, go to plus infinity. Pointing down, go to minus infinity. Clear with this? There you can, we have seen more variations of this. We can even do for I and 4i also. You can check out the electrostatics. We have seen these kind of problems there. So this is one thing based on graphs. Then let's say we have a spiral. Inner radius is A, outer radius is B. All are carrying current I. N turns tightly wound spiral. Find the magnetic field at the center. Hope you remember the technique for spirals. Let's see. Hmm. You know the theme here. We take a radius x, thickness dx. So number of turns in this dx will be the total number of turns by width nb minus a into dx. So the magnetic field due to this one dx will be mu naught I by 2x, mu naught I by 2r into number of turns in dx. Therefore, the magnetic field at the center that is b minus a. Integral dx by x, limits will go from a to b. You, for the direction, you can use the right hand thumb rule and it'll be out of the plane. Clear with this? So whenever you see a spiral, this is the theme there. Get the radius x, find the number of turns per unit width, get a dx thickness, and finish it off. Any doubts on this? All clear with this? Next one. We have a random charge sheet. Sigma is your surface charge density. This sheet starts going in the xy plane about the z-axis with omega. The shape of the sheet, I don't know. Area is not, nothing is given. The electric potential of the sheet about the origin is given. Last class we have seen if a charged particle goes in a circle, it behaves like a current loop. If you have a current loop, you get a magnetic field. So this thing behaves like some current. So find the magnetic field at the origin. So there is some relation with the electric potential. The distance of the sheet is not given. Area of the sheet is not given. You only know omega, you know, or potential, you know, sigma. Your answer should come in terms of these terms. How do we proceed with this? So consider some random piece here. dq. We know how to find for dq. So the current due to dq will be charge, which is dq by time, which is 2 pi by omega. This small current will produce a magnetic field, which is going in a circle, mu naught I by 2 small r. I don't know r, I don't know dq. This will be mu naught omega dq by 2 pi by r. So when you try to integrate this, you end up with mu naught omega by 2 pi integral dq by r. Great. I don't know dq, I don't know r, but if I multiply this with mu naught omega 4 pi epsilon by 2 pi, and this thing will be dq by 4 pi epsilon r. Now suddenly that becomes potential due to the dq, isn't it? This term here inside is the potential, electric potential due to dq. And potential is a scalar quantity. So if I integrate this, I'll get the total potential. So your formula becomes mu naught omega. That is a 2 pi there. I missed something. There is a one more 2 sitting here. dq mu naught I by 2r and 2 pi r. So that would be 4 pi. 4 pi cancels off mu naught omega naught epsilon b. That's your formula, everyone. Pretty good result. V is the potential due to the sheet at center. That means if I know the electric potential, I can find the magnetic field in case something is rotating. Clear with the result? Do you know how they'll frame a question on this? The question would be of something like this. They will say, this is the top view. We got a disk. Remember, this formula is valid for plane sheets in this thing. Plane sheets rotating in a plane. Vehan, what are you talking? You will use wherever you want. That's it. Matlab, there is no reason, no head and tail for a logic there. Why didn't you do that in gravitational field and electrostatics and everywhere? Why did we study so much then? इतना काम क्यों करना है ना? Directly use कर ले सब जगह. Na? For a ring, current I is flowing. So center of mass is the center. Assume there's a current I. Solve the problem. Let's use center of mass for everything. There is a head and tail. There is a reason why you can use it some places, why you can't use it some places. Do you know what is the reason?
1 by r, sir.
What is the reason?
Sir, it's 1 by r, not r. Means
What is the reason?
sir, it's not in that form where we can use it that r dq or the empire. It's not
It will
directly
be a
a
linear function. Then clear with this. So there. So we have a charged disk which is hinged at point A and it is rotating about that. So they'll ask you find the magnetic field at A. This would become an advanced question. Remember, you can use center of mass only if it's a linear function. Potential is 1 by r. So anyone remembers the potential for this? In electrostatics, ये क्वेश्चन था याद आया? Potential to disk at the corner. This one, sigma r by pi epsilon. This we did in electrostatics. So they'll combine things like this. So always when you use stuff, understand, ask yourself, because exam I won't be there to correct you guys. If you're jumping into using some shortcut or something, ask yourself, is the shortcut valid here? Can I do this thing here? There. So you're done. So formula will be mu naught epsilon naught omega VA. If you know the potential, you're done. Now it looks easy because you know VA. That finding VA itself is another headache, isn't it? A is a point on the circumference. So we combine two of these things, that and this. Suddenly this becomes a really good question. Clear with this? Any doubts on this? This is a kind of a problem which looks scary and tough, but is actually easy to solve if you, I mean, you have to get in terms of potential. Next one. Let's say we have a semicircular cylinder. This is going till infinity. Infinite semicircular hollow cylinder. So here current is flowing out of the thing like this. It is coming out. It's flowing along the surface. Hope you're able to visualize how it is. The total current is I. This is your axial line. This is your radius R. So if you actually see the top view, the current here is coming out of the plane. Let me draw it like this. Find the magnetic field on the axis. Hmm. It's a half hollow cylinder. I pi square R. Looks right. Let's see. Right, Niharika. Let's see whether you got it. So what we do here from the center at an angle theta, take a thin slice d theta. So this itself will be like a small current here, I. So it's like a infinite current wires, which is current by total circumference I by pi r into r d theta. This is the current in that small d theta. This is behaving like an infinite wire. So if this is the current infinite wire, put your thumb outside and try to rotate it. You will notice the field is going like this. The field is going anti-clockwise. So the field B bar is like this. This angle will be 90. This is your dB. This will be 90 minus theta. So dB will be mu naught I by, it's an infinite wire, 2 pi r. So dB bar, the vector form, will be mu naught by 2 pi r. I will be, rr will cancel, I d theta by pi. Cos 90 minus theta, that will be sine theta I cap plus cos theta j cap. Since you're taking theta from the center, limits will go from minus 90 to plus 90. So B on the axis will be mu naught I by 2 pi square r sine theta d theta minus 90 to plus 90. Both the angles are going in the opposite direction, I cap. This will become cos theta, cos 90 is 0. This will be cos 2 theta minus pi by 2 pi by 2. Only the j cap components add up. That comes out to be 2. Mu naught I by pi square r. Check. The direction is only j cap. You can actually kind of get the direction. If you take one more angle here, what about this magnetic field? This will be like this, na, dB bar. Can you see horizontal components cancelled, only the vertical components add up. There's a symmetry. Check this out. So you can treat each section RD theta as infinite wire. Find the field due to infinite wire. Remember, always when you integrate vectors, you have to integrate I cap and j cap separate. You just can't integrate the magnitude, because each part ka dB bar is in different directions. Clear with this? Any doubts on the integration, please ask. Anything on how did I choose the element? Anything, any other confusion? Clear, na, Pushkal? Vihan? Om? Devansh?
Sir,
Aditya? Saish? Devansh.
sir, ये infinite है कि semi infinite?
It's an infinite. This side is also infinity ray. I can't draw the whole thing ना. Current कैसे दिखाऊंगा मैं? How will I show you the current? If I show the current in the middle, you will understand. It's coming out of the plane. It's an infinite. Clear? I can understand. Picture is, I can't draw that, but ठीक है. Next thing. We have an infinite plate. This is going to infinity. L is the width of the plate. So here current is flowing like this. We have a point P here at a height r from the center of the plate. If you look at this in the side view, this is that L. So current is going into the plate. Are you able to visualize? Think of like this. If you see my screen, it looks like this. Can you see the book? This is the infinite plate. Current is flowing like this. It's going along the surface. This width is L. And the point P is somewhere like this. This is point P. It is at a height r from the center of this thing. Able to visualize? That is how your plate is flowing. Plate is there. So from the center, the point P is somewhere here at a height r. This is how the side view will look like. We define K, which is current per unit width. That means if you take a small piece dx, the current in dx will be kdx. So you can treat that as an infinite wire basically. This is an infinite current carrying plate. Plate is long, infinitely long, but it has a width. Current flows along the surface as shown. Find the magnetic field at point P. P is a point above the surface from the center. P is at a height R from the center of the plate. Then in the end, we'll put L is infinity. Then it becomes an infinite current sheet. Remember, infinite charge sheet sigma by 2 epsilon, we will get that result. That would be a pretty good mains and bits level result. But this thing would be how they can ask you a finite sheet. Try. I'll give you 2-3 minutes. How do we start? So if you look at the side view, at a distance x, if I take a thin slice here, the current will be kdx. So this thing is behaving like an infinite wire. If you look at the field direction, this is the distance, let's call it r. It will be like this. It is going clockwise. Agreed? That's your dB. Similarly, if I take one more piece on the other side symmetrically, this also you will notice will be something like this sort. This comes out like this. You can clearly notice here theta and theta. This will be theta. That would be 90 minus theta and 90 minus theta. So only the horizontal components will add up, the vertical components cancel out. This distance is r. Great. So the magnetic field will be mu naught I by 2 pi smaller. The magnetic field at point P will be integral dB, only the horizontal component cos 90 minus theta. These components will integrate. Limits will go from minus L by 2 to L by 2. Because you're taking x, right? Distance, so minus L by 2 to plus L by 2. This will be dB is mu naught. I will be k dx by 2. R is nothing but, wait, this is already R, na? Let's take it as some Z. Z is root over R square plus X square. This will be 2 pi root over R square plus X square, and that is sine theta. Sine theta is another R by root over R square plus X square. This will be mu naught k by 2 pi R integral dx by x square plus r square. That is nothing but tan inverse 1 by r tan inverse x by r, isn't it? That's a tan inverse integration. You can do integration by substitution if you want. Put x is equal to tan theta and you can solve from there. This thing turns out to be mu naught k by 2 pi r 1 by r tan inverse x by r, limits minus L by 2 to L by 2. RR goes off, you'll end up with 2 also will goes off. You will get mu naught k by pi tan inverse L by 2r. Check. Meaning the moment you wrote this dB thing, right, it is over actually. It's all max after that. Like he keeps saying, math physics the only headache is how to get the element, which part to integrate. If it's a vector, divide I cap, j cap, and then do all that. We're not integrating the vertical components, they'll cancel out anyways. You could have done that also. Integrate dB sine 90 minus theta, I would have got zeros. Clear with this? So let me put this result again. So if you take a finite sheet like this, again, from the center, if you take this point P here, the field will be this way, which is mu naught k by pi tan inverse L by 2r. Now here, if you make L tends to infinity, suddenly you make it an infinite sheet. This will be the side view, going till infinity, going till infinity. So if you look at the field here, this will be mu naught k by 2. The tan inverse 90 becomes pi by 2. This will become mu naught k by 2. Can you see the resemblance? It looks like sigma by 2 epsilon. Sigma का place में k, epsilon का place में 1 by mu naught. And best thing, this is constant. Definitely remember this result. It's a direct main scale question. Now, how do we get the directions though? For direction, it's pretty easy. This is how you can remember the directions. Suppose if someone gives you like this infinite sheet, choose any one wire, okay? So let's choose this wire here. For this dotted line, how is the field ka direction? Put your thumb out and rotate. So isn't this the direction? Isn't it? If you take your thumb and rotate this, this will be a anti-clockwise direction. That means the field here is this way, mu naught k by 2. Field here is this way, mu naught k by 2. That's it. Take any one wire, see the direction of that field. That will be the direction of everyone. Suppose if I put something like this. What do you think will be, let me put cross. What will be this direction? So take any one wire. This direction will be clockwise, isn't it? This way and this way. Magnitude is easy, mu naught k by 2. All clear with this? There. So do remember that result. So mu naught k by 2 and the direction is given by choose any one wire and find the direction. If it is rotating right, then all the fields will be right. So the fields will be opposite directions. Clear? So let's do a question based on this. Let's say we have two infinite current sheets. This is K. This is 2K. Draw the magnetic field lines. Along XY and YZ plane. A simpler question would be this. If I choose 4 points here, A, B, C, D, get the magnetic field at A, B, C, D. Start from there. If you got the directions, you can draw. And we have done this before, something similar. Remember? Electrostatics में था. No, we did this in Gauss law. This question. Remember this? Field lines and the equipotential surfaces. Get this, you got a minute. So the red one ka field will be this way, mu naught k by 2, mu naught k by 2. The green one ka fields will be this way, mu naught k, mu naught k. So this will become up. So the field length will look something of this sort. You can get this angle theta. Tan theta will be opposite side, where this side tan theta is 2. And here field length will be like this. Here field length will be like this. Here field length will be like this. You can draw multiple of them. You're getting how the field lengths? They'll find the rhombus ka shapes. Won't it be opposite for the red? Red will be opposite for the red. I goofed up. Shit. Take this as theta, tan theta is 2. Clear with this? This is how they would kind of look like. Clear with this? Next thing. Let's say we have an infinite charge sheet. Sigma is the surface charge density. And this whole sheet is moving with speed v. You kept a block here of mass m. Gravity is there. Find the normal reaction. The block also has charge plus q. Block of mass m with charge q is placed on a charge sheet moving with constant speed. Find the normal reaction between them. What's the catch here? What are all the forces that are acting? First of all, what the hell is with this charge sheet actually? Charge sheet is doing two things. One, it is creating electric field. That is fine. But when this thing started moving, remember, a moving charge behaves like a current. So the moment this thing started moving, this thing started behaving like a current sheet, isn't it? Infinite current sheet. So this thing is like an infinite current sheet going with speed v. So consider some charge here. So what is current? Let this width be, let this be L. I know it is infinite, but let's see it is L. What do we get? And let this be some area here. So current will be sigma into area of this cross section. Area that will be charged by time. Let me show it like this. So this is like a current which is coming out. That is what it feels when the charge is moving. So consider a thin cross section. Let this width be dx. Let this be current I flowing here. I is nothing but dq by dt. So here this will be sigma. L is the length. L dx by dt. Now here, be careful here. There's a catch bit. Dx by dt is not v. There's something I'm missing. Let this thing be some dx. Let this be some dy. Dx by dt is not v. That will be wrong because x and d are not in the same direction. Wait, I am not taking the element properly. Let's not make it so complex. Let's take a small element. That's better. Let's consider a small piece here like this. Like this. This is your dx. This is your width w. This is your dy. And this piece is going v forward. Perfect. Great. So what is dq? Dq will be sigma into surface area, which is dx dy by dt. So we get current as sigma dx by dt. This is velocity because it is dx is in the direction of velocity. But what you want is current per unit of width. That is I by dy. This will become sigma into v. Clear with this? This is current per unit width. Basically, this is your kk value. Clear? So this whole sheet is behaving like an infinite current sheet where current is flowing like this. If the current is flowing like this, how will the magnetic field be? B will be parallel to the sheet, which is mu naught k by 2. Got it? On top of it, you also have electric field, which is pointing upward, which is sigma by 2 epsilon, because it's a positive charge. Now, if you draw the FBD of this block, you will see the forces mg acting downward, normal reaction acting up. And remember, this block is also going forward with v because it is on the sheet, it's moving with the sheet. So there'll be a force qv cross b. So there'll be also magnetic force, which is downward. This will be F magnetic, QV cross B. And because it's also positive charge, there's an electrostatic force, which is EQ, which is sigma by 2 epsilon Q. Therefore, the normal reaction will be mg plus qvb minus sigma q by 2 epsilon, where b is nothing but mu naught k by 2. And k is nothing but sigma b by 2. Clear the steps, everyone? So when you take the surface area, you should take this area. Sigma into area is the charge. So charge is on the surface. That W is actually kind of useless, but okay. Clear with the steps? So that when you have an infinite charge sheet moving, it behaves like a current sheet whose K will be sigma into V. There's a current per unit width, and yeah. Clear with this? So that's a little bit about the infinite sheets. Take a small break. Come back by 9:37. We'll continue from here.
So,
Vihan.
so in the question it said that the sheet is moving, just the sheet.
A block of charge is placed on a charge sheet moving with constant speed V. It is moving with the sheet.
So then, wouldn't it be like we would not observe any magnetic effect, like when we add
Why?
the charge with the wire?
There's a constant magnetic field everywhere in the space. It's an infinite sheet.
Okay. So infinite sheet is moving with V. It
And the
is
block is
causing.
placed on the sheet. The block is also going with the sheet. ठीक है, लिख लेता हूँ भी. Happy?
Okay.
So we have a charged particle which is projected towards an infinite current carrying wire. As it gets closer and closer, the magnetic field becomes more and more. So this thing will start deviating. So find the minimum distance between the wire and the charge. So charge Q is projected towards an infinite wire. From distance d. As you get closer, the magnetic field increases. If the magnetic field increases, QVB increases. That means this thing will start deviating. So it will go in some weird path. This will not be a circle, non-uniform magnetic field. So what is the closest that you can approach? What remains constant? Something remains constant. Anyone? So let the velocity be Vx I cap plus Vy j cap. Speed remains constant, not velocity. Velocity will change direction because work done by magnetic field is zero. And there's no other force here. The work done by magnetic field is zero. Therefore, speed Vx will change, Vy will change, but the resultant will remain constant. So let's say it is at some distance x. At this point, if you see the magnetic field, it is out of the plane B, which is mu naught I by 2 pi x. Your velocity v is in some direction. The force acting on this will be QV cross B. This will be QV cross B K cap. So when you do the cross product, I cross K cap will give you minus J. This will be Q Vx mu naught I by 2 pi x. I cross K is minus J cap plus QVy mu naught I by 2 pi x. J cross K will be I cap. We will take the I cap ka component because when this guy is taking a turn and leaving here at x minimum distance, that means you stopped going towards it. All the velocity Vy will be u only. And Vx will be zero. Do you agree? There will be no velocity component towards the wire. That's why it will start taking a turn. So take the horizontal component will be Max will be Q mu naught I by 2 pi x Vy by Vy. So Ax will be Q mu naught I by 2 pi m. Vy is nothing but root over V square minus Vx square by x. I'll substitute Vy with this guy. This whole thing is a constant here. I'll just call it some, let's call it some z. And then we can integrate this. So if you integrate this, this will turn out to be Vx dVx by dx is equal to z root over V square minus Vx square by x. Shift everything to one side and then integrate this. Vx dVx by root over V square minus Vx square is equal to dx by x into z. Integrate on both sides. This will Vx will be initially V to 0. This guy will be d to x minimum. This we can do integration by substitution. Put V square minus Vx square is equal to t square. This will be minus Vx dVx is equal to t dt. Substitute there. If you put the limits, Vx is equal to V, this will go from 0 to V. This will become minus t dt by t. This will be z ln x minimum by d. This will become x minimum is equal to e power minus v by z into d. That's your answer. Z ka value, you can substitute that. What is Z? Q mu naught I by 2 pi m. It's an exponential decreasing function. The faster, as you get closer and closer, it will take a turn. Technical equation is done here. Then just a matter of integration. Look at the steps. If you got this page, then you're done. The remaining is just math. Clear with the steps. Why we didn't take Vy? Vy, you could have taken it, but there is no use actually because you want x minimum. Vy's won't help you. That will give you dy, y coordinate, isn't it? We don't need it. So that is the only reason to take ax. This will not go in a circle. This will be completely a weird path. You're getting everything in exponentials. Things will go pretty messed up, I guess, if you try to find x and y coordinates. So anyways, any doubts on this? Next one. There. So we combined, the QV cross B magnetic force with the magnetic field of an infinite wire. You'll get combination questions like this. We have a charged ring. Plus Q and radius R. Rotating with omega. On the axial and at point P, at a distance of R root 3, there is a point P. Find the ratio of electric field by magnetic field at point P. If you have a charged ring, it creates a magnetic field, it creates an electric field. And if the charged ring is rotating, it will create a current, and that current will create a magnetic field. Find the ratio of electric field and magnetic field at point P. Distances are root 3, and use this result. 1 by root mu naught epsilon naught is equal to 6 speed of light. So answer should come in terms of speed of light. You will not find mu naught epsilon naught in the options. And that's what makes this question really good, actually. Most people will figure out the ratio. They'll not understand how you got speed of light in the options. This we will see later on in current electromagnetism, EM waves. But you should know the result though. Hope everyone remembers the formulas for electric field and magnetic field. First of all, what is a current? Current is nothing but charge Q by 2 pi by omega. So the electric field is given by KQ, X is R root 3, by r square plus x square. I'll do one thing, I'll just keep it in x. Kqx by r square plus x square whole power 3 by 2 by the magnetic field mu naught I r square by 2 r square plus x square whole power 3 by 2. So the denominator goes off. You will simply end up with kqx. The 2 will go up by mu naught I r square. You know everything, substitute. 2k. K is what? 2 by mu naught I r square. K is 1 by 4 pi epsilon. X is r root 3. I also need to substitute. Root 3 and I is nothing but q omega by 2 pi. You end up with the q cancels. R square में 1 r goes off. 4 pi goes off. 1 by mu naught epsilon root 3r by r omega. That's nothing but c square. Root 3 c square by r omega. Check. Clear everyone? 1 by root mu naught epsilon naught will be c square. That is a ratio of e by b. So for different points, you'll get a different ratio, but the denominator always cancels off. So e by b is actually proportional to x, the distance. There, we combined electrostatics ka formula with the magnetic field ka formula. Now, based on this field on the axial line, this is your fifth shape. The first shape was your finite wire. The second shape was your arc. The third shape was this thing, field on the axial line. The fourth was infinite plate. The fifth shape is a solenoid. So finite solenoid, this thing is nothing but like a spring, a helix. There's a tightly wound coil. There's no space between them. I didn't draw it properly. It's a tightly wound coil. Small n is the number of turns per unit length. Example, let's say if someone makes a coil 3000 turns, let's say this is 2 meters, then your n will be 1500 turns per meter. So this thing dimensions is 1 by length. So tightly wound coil, you can think of this thing as like a spring. Spring is a good example. Spring is a solenoid helix basically. And in this, we have a current flowing now. I is the current which is spiraling, meaning which is going in a helix. So you take this shape. So on the axial line, let this be radius r. Let this be length L. So take a point over here. So from here, if you go to the corner, and from here, if you go to the corner with the vertical, this angle is beta and this angle is alpha. So is a point on the axial line which makes angle alpha and beta with the vertical with the two corners. So if I make alpha is equal to beta is equal to 90 degrees, it becomes infinite solenoid. Find the magnetic field at point O. One thing that you can do this kind of problems, right? You can treat each coil like one ring. So you can treat them like multiple rings, very close to each other. So basically I can use the field on the axial length formula. And then I can integrate all the rings from whatever is the length. So question would look something like this. So that O is here. So you will take a multiple rings here at a distance x. And then you try to integrate this. Try. I'll give 2-3 minutes. Again, this thing looks complex, but integration is also is easier with this. This is your fifth shape, a finite solenoid. See, all this infinite solenoid, infinite plate, these are standard results which you should definitely remember for the mains or bits or these kind of exams. Advanced may, they will expect something of this sort. They will change up the shape or they will do a part of the shape. They'll mess up. You should know how to integrate the terms. Others, you need to keep your cams on. Let's see. So this is your point O. At distance x, take a small thickness dx. It's called, there won't be one turn there. There'll be multiple turns here. So we don't know how many turns are there in that. So number of turns in dx will be small in dx. Small n is the number of turns per unit length. That is given. You're taking angle with the vertical. So let's take this as theta. This is theta. So your theta limits will go from alpha to minus beta. And theta is x by r. The radius is r. The magnetic field will be number of turns, which is n dx. The field due to each one will be mu naught I r square by 2 into r square plus x square. And dx will be r sec square theta d theta. So if you substitute here, you will end up with mu naught n I r square by 2. Denominator will be r square is x square 3 by 2. That will be r cube. 1 plus tan square theta sec square theta. That will be sec cube theta. Numerator will have another r sec square theta d theta. So we get a mu naught and I, R goes off. You're just left with cos theta minus beta 2 alpha. There, you get field at point O will be mu naught ni by 2 sine alpha plus sine beta. That's your result, everyone. If you take alpha is equal to beta is equal to 90, it becomes infinite solenoid. In real life, you won't get infinite solenoid, but what it means is the length is much, much greater than radius. If length is 2 meter and the radius is 2 centimeter, you can take it as an infinite solenoid. Then your field becomes B is equal to mu naught Ni by mu naught Ni. And the best thing about this result, later on we will see in Ampere's law, it is just not at one place, it's constant everywhere. The entire solenoid instead will have a constant field. We will prove that in Ampere's law. There, it doesn't depend on the length or the radius, it just depends on the current and the number of turns per unit length. That's your infinite solenoid. Quite a useful result. You should definitely remember this. Clear how we derived for a finite solenoid? Next one, any doubts on this? The main thing is still here. If you got dB, then you're done. So even though here we derived only on the axial line, but for an infinite solenoid, it will be constant everywhere. We will see that. So based on this, let's say if you take a conducting spring, basically a solenoid. And let's say you start sending current in this. This is a conducting spring in natural length. So let's say case one, you send a constant current. Case two, you send a AC current. Basically, I is equal to I naught sine omega t, something like this. This is an alternating current. Current is fluctuating. What happens to the spring? Examining options will be like this. It will compress, it will elongate, it will oscillate. It will compress or elongate depending on the direction of the current. ऐसा कुछ options होगा. Two questions. What do you think will happen? Think it's a theoretical one. Okay. Let's see. Yeah, Aditya. First one is wrong though. Let's see. Spring will move. Spring will not move. Nothing will happen. Okay, let's see. So like I said, you can treat each one like a ring of its own. I mean, all of them, the current will flow in the same direction, clockwise or anti-clockwise, whatever it is, it doesn't matter. That means, if you remember, I told you this also, the magnetic field lines will be coming off like this. Or maybe the other direction. It doesn't matter, it is the same thing. But it will be same for all of them. That means I can treat these things like magnets. North pole, south pole, north pole, south pole. Do you remember this? Last time I told you, if you have a coil, it behaves like a magnet. Suppose if the current is going in the other direction, then what will happen? It will be north, south, right? So if you change the direction of the current, only the magnets ka thing will change, but still north, south will be there. And if you look at this orientation here, this north and south will attract. This north and south will attract. This north and south will attract. If the current is going the other direction, they'll still attract. So it doesn't matter how the current flows, they'll always attract. So in case one, the spring compresses. So when you send constant current, it will just compress and stay there. Nothing happens. But if you send AC current, when the current is flowing, it will compress. When the current goes off, it comes to natural length. Remember, in this case, it will never elongate. There is no case where this will elongate. It compresses, then it comes to the natural length. As the current becomes zero, then again it will compress. Again, it will come to natural length. It will be a cycle. This will start oscillating. So compress, natural length, compress, natural length. It will not elongate. But if the spring has some mass, maybe due to inertia, it might elongate a little, but it won't elongate as much as it is compressing. Right? So in this case, it will oscillate. This is what actually you observe, if you ever been beside a transformer, not the Optimus Prime wala transformer, we're talking about electrical transformer, the current one. So if you actually see a transformer, right, inside it is actually made of coils. You'll have huge number of coils. So if you go beside a transformer, you'll hear a buzzing sound, buzz. There is a sound, continuous sound which is coming. That happens because current has a frequency of 50 hertz. That is 50 cycles per second. So these coils are actually compressing, expanding 50 times per second. So that will give a 50 hertz ka constant sound. That buzzing sound which you hear is because of these coils compressing and expanding. To reduce this, they fill up with this oil and all, but still there's a little buzzing, if you're getting it. So normally there's not a big deal, but when you install transformers in outskirts, right, these vibrations travel through the ground and they attract snakes. The snakes which are going in the nearby area, they get attracted to this vibration. It's like the transformer is calling them, come here types. And they go to the transformer and they love the transformer because transformer also produces heat. And the snakes are cold-blooded animals. They want heat. They'll go there, they'll sleep in the transformer. They'll think, yeah, this is a beautiful place to stay. It is hot, it is calling. What else you need? Sometimes the transformer gets short-circuited because of the thing and transformer explodes. Snake dies, but transformer also goes off. Sometimes the snake finds a way to stay inside. So when someone goes there to do the maintenance for the transformer, they realize there are a lot of snakes surrounding it. So when they install a transformer, they build a big base, they fill it with sand and the railway station mein hote na, stones, damping effect. So basically they try to reduce the vibrations. But there is always a possibility a snake is there. If you are installing one in a forest area, there is a high possibility. So Mumbai, there is no possibility. Humans only don't have place. Where will the snake come from? So that way, by chance it comes, to unfortunately it will die also. Snake karke people will jump around and stamp it. Anyway, so that is a little, look at this thing. This is actually, if you see, right, it's like kind of like a solenoid. You can see the coil there. So you're sending a huge amount of current there and you're putting a metal piece there. So it gets, there's like a magnet there, so it's repelling. Can you see how it is floating in the middle? So if you leave it like this for some time, right? There's something called eddy currents. We will see that in the next chapter. These eddy currents start, generating in that metal piece, and it starts getting hot. And you leave it for enough time, it actually starts getting heated up. This is what they actually use in, electric furnaces in factories. In the steel factories and all, when they get this iron ore and everything scrap, and they want to melt it, they use these eddy currents to melt it. Efficient, no need of any coal or anything. All you need is just current. There are no moving parts, nothing. Pretty convenient, and you can generate huge amounts of heat. That thing can literally melt. This is another thing which I liked. I tried making it, but I couldn't make it properly. So there, he made a spring. So he's attaching, that's a neodymium magnets. They are pretty strong. You will get them in Amazon. They're a little expensive also than normal magnets. I think those small pieces which you're seeing, each one will cost you around 100, 200 rupees, I guess. You might get it cheaper also. When I brought it, was too expensive. Anyway, so he brought two magnets, he keeping them on both the sides. So neodymium magnets, right, is a rare earth metal. They're also conducting, and they're also pretty strong magnets. Now, initially, when you keep it inside, one is a positive terminal, one is a negative terminal. So technically, there's no current now. But the moment you put it in the spring, they will touch that metal piece, current will start flowing through the coil. Once the current flows through the coil, it will generate a magnetic field because it is a solenoid. That magnetic field and this magnets will get repelled, and this thing starts moving. So look at this. There are no moving parts, nothing. Just goes off on its own. And if you close this, there you got a spring. Basically, it is literally the concept of maglev. So in maglev, you don't even touch the metal blood, you're just floating. So you get the magnetic field from external source. There are two trains now, see. And the best thing, the train behind is pushing the other train due to repulsion. Those magnets are really strong. If you leave them from little distance, they'll hit each other and they'll break into pieces. This guy is really having fun though. That's how you can. That's a solenoid. So I can't show you magnetic field. It was solenoid, but that's the thing. The biggest headache in making that is that spring thing. I couldn't make it. Because when you go to a shop and ask for a copper wire, most of them will give you an insulated copper wire. So the copper wire will have a plastic coating. First, I didn't realize that. If you have a plastic coating, what will happen? Even if the magnet touches, your current won't flow, na? So you need to get a wire without any insulation on the top. And second, once you get the wire, it should be sturdy enough to make into a coil. And second thing, the coil should not touch each other. If it touches it, will get shorted. So yeah, making that coil was a pain. But it is doable. Maybe I didn't know how to do, or I didn't have the proper equipment, but it could have been done. Anyway, so that is a little about solenoid. Again, we'll encounter the solenoid later on. It will come, and when you do it in Ampere's law. So next thing, force between parallel wires. This is easy. There's nothing there. If you have two current carrying wires, I1 and I2, and the distance is d between them. So how do you find the force on each of them? You find the magnetic field due to one guy. So this will be the field due to one guy, which is mu naught I1 by 2 pi d. Then we use the force curve formula, F is equal to IDL cross B. That will be I2, this will be DL, and this will be B1. So we get force per unit length is mu naught I1 I2 by 2 pi d. There, if you keep two parallel wires, this is the force between them. Force per unit length. Quite a useful formula. Especially this formula is really useful to find the dimensions of mu naught. In units and dimensions chapter, if they ask you find the dimensions of mu naught, this is one formula where you have full mechanics ka terms, if you see. Every other formula will involve something which is more complex. So remember this formula for that sake. If you want to find the dimensions of mu naught, this is the formula which you can use. If the current is flowing parallelly, they will attract. If the current is flowing opposite to each other, the wires will repel. You can check it out from the directions, IDL cross P. There, easy formula. There's nothing there. So let's see a question on this. Clear? We have a infinite fixed infinite wire. At a height T, you kept a wire of mass M and length L. This is movable. Gravity is also there. Let the current go in the other direction. So basically it is getting repelled. Find M if the wire is at rest and find time period for small oscillations. That is the actual question. So this infinite wire is repelling that small wire. That's why it is at rest. So it is in equilibrium. So if you disturb this, this won't keep quiet. This will start oscillating. Find time period for small oscillations. That is the main question though. Anytime you hear the word equilibrium at rest, SHM is always there waiting. It's like normally whenever there's an earthquake near a beach, there is always a chance of a tsunami. If earthquake doesn't kill you, tsunami will. So if equilibrium doesn't kill you, SHM will come. Let's get this. So what is the mass? That is easy. So if you see the gravity will act downward, the magnetic force will be upward. F is equal to mg. So this will be mu naught I by 2 pi d into L is equal to mg. That you got your m value. Then how to do SHM? Always displaced by x. The moment you displace this by x, now the force will change. This will become F minus mg is equal to ma. Now the force becomes mu naught I length L by 2 pi d plus x. Basically, the magnetic force has decreased because the distance increased, but mg is still there, so it will pull you down. It is a stable equilibrium. But we know mu naught I L 2 pi d is mg. Take out d common, you'll end up with mg by 1 plus x pi d. You can do binomial approximation, g minus x by d. We get a is equal to minus g by d into x. This is your omega square. Time period is 2 pi root over d by g. Yeah, SHM, that's how you always start. Once you find the equilibrium, displace it by x on either side, and then find the restoring force is equal to ma. So here, when I push it up, the magnetic force will decrease, but mg is still strong, so it will pull it down. If I push it down, the magnetic force will increase, then it will push up. So that will just keep oscillating. Again, for small x, because or else you can't do the binomial approximation. Clear with this? This is for parallel wires, but every time you won't be lucky to get a parallel wires. What if you have a infinite wire I and you have a perpendicular wire like this? So exam, what they'll ask you? They'll ask you in which direction does that small wire move? In which direction does the small wire move? In which direction does it rotate? So options will be like this. It will go up clockwise, it will go up anti-clockwise, it will go down clockwise, it will go down anti-clockwise, it will go right clockwise, right anti-clockwise, left anti-clockwise. Aisa. They'll make options of that sort. So in which direction does this wire move and rotate? This wire is fixed, infinite wire is fixed. Get them? Let's see. So at a distance x from here, take a small dx. The magnetic field here will be downward, which is mu naught I by 2 pi x. So the small force will be I dx b, which is mu naught I by 2 pi dx by x. Therefore, the force will be mu naught I by 2 pi. That will be ln x limits will go from L plus d by d. That's your force. But if you look at the force on this wire, you will notice something. The closer the wire, the higher the force. So as you go to the right side, the force is continuously decreasing. There is more force on the left compared to the right. So this will give a tendency of this thing to rotate clockwise. Clear with this? So this thing moves upward and rotates clockwise. Right, Om. Clear with the forces? Easy one. It's a good question. So if you keep a perpendicularly, this is how you will get. So this is only for parallel forces, huh? Mu naught I1, I2 by 2 pi d. This is if they're perpendicular. What if I have even something better? What if you have a current wire here, I, infinite wire out of the plane? And let's say you bring some random wire like this. This random wire is carrying current I. The wire is in xy plane, and this coordinates are x2 comma y2, and this coordinates are x1 comma y1. That we only know the coordinates and the currents. Find the force between them. Find the force on the curved wire due to this infinite wire. This is a good one, right? This is a little non-standard one, but the final result we get is pretty nice. We will see it will be independent of the shape of the wire, but let's see how will we get that. Think for a minute or so, because this is a little different. We have to use something called polar coordinates. Let's see. So just choose any random point on the wire. I'll do one thing. I'll take I in the opposite direction. It doesn't matter, just for convenience. So if you look at the magnetic field here, this will be in this direction, dB bar. And if you could look at your DL bar, DL will be in this direction. That's your DL bar. Now in polar coordinates, you remember, I hope you remember this. We have done this in basic maths. We also have seen bits of it in electric dipole. So in polar coordinates, we have two directions. Remember, a vector can be always divided in two perpendicular directions. So instead of taking x and y, we will take the radial direction, r cap, which is dr in that direction, the tangential direction, which is r d theta, theta cap. So you can write a vector dr bar or dl bar as dr r cap plus a tangential length is r d theta, theta cap. A radial vector and a tangential vector. There, we divided the vector in two components. Then we know the force dF will be I dl cross b bar. This is I, so dl is dr r cap plus r d theta, theta cap cross here b ka direction will be mu naught by I 2 pi r. I don't know the thing here, but this also will be theta cap. Agreed? The magnetic field is also tangential. Magnetic field is always circular, na? So b bar is always tangential. So here b bar, actually that will not be db, it is just b only. Mu naught I by 2 pi r theta cap, tangential direction. Theta cap cross theta cap will be 0. R cross theta cap will be k cap out of the plane. Isn't it? You can see the cross product here. R cap is this way, theta cap is this way. R cross theta cap will come out of the plane. So this will be I mu naught I by 2 pi dr by r k cap. There. So if you integrate this, we get f is equal to mu naught capital I small I by 2 pi ln the distance rb by ra k cap. That's your result, everyone. Pretty neat result. So it doesn't depend on the shape of the wire, it just depends on the distances. So in our question, the answer would be, so here RA, RB, you can calculate. Root x2 square plus y2 square and x1 square plus y1 square. So you know how they'll frame this question? They'll give something like this. They will say, we have an infinite wire here, I, and they'll say there is an elliptical wire. X square by a square plus y square by b square is equal to 1. This point is a comma 0 and this point is 0 comma b. Then they'll ask you find the force on it. You will die calculating that normally if you try to do. But if I know this result, mu naught I by 2i, this is simply ln a by b. And the best thing about the result, most people will focus on the ellipse, but think technically it doesn't matter what wire you take. The answer will remain same. That ellipse is a trap. Most people will see that ellipse and think, oh, ellipse se kuch karna hai. The ellipse is useless. You could have taken any random wire, the answer would have been still same. Clear? Pretty good thing. So there, instead of doing in terms of I cap, J cap, you do in terms of theta cap and R cap. So not a mains type of question, but yeah, advancement is a pretty good one. The result is pretty nice. That's the reason I showed it to you. It doesn't depend on the shape of the wire. It only depends on the starting and the end point. But unfortunately, we can't use anything like projected length here. Clear with this? At least remember this, right? That it does not depend on the shape of the wire. So if you give me a question like this, you know, what is the first thing I will think of? The moment I see this random shape, I'll be very happy. One thing I'm clear, that means it doesn't depend on the shape of the wire. That means no matter what shape I take, the answer must come same. Right? So then I will try to do something like that. Maybe I will try to put a triangle here, or maybe I will try to put an arc here. I will try some things and try to figure out the force. Getting it? You can play around like that. And if you can get the answer for that, it will work out. I would try, but yeah. One way to do now, I would have done like this. Maybe I will draw a circle like this, because on a circle I can find the force, because B bar and I are parallel. Then I can find the force on this part, the perpendicular one. Then I can add these two, then I get the resultant force. So I will do something of that sort. So keep that in mind. In case you don't know, the moment you see, this is the kind of things you will know when you practice a lot. When you see different models, you will realize the equation of the wire is not a given. So that means it doesn't matter what I take. So I will take something which I know how to do and I'll get the answer for the exam sake. But yeah, when you're learning, you learned it. Clear with this? There, that is the last one for that day. So next class when we catch up, we'll continue from here. We will see a few more models on this and we'll go ahead with Ampere's law. But on Friday, I think we will wrap up the chapter. Mostly it will be done. We are mostly almost there. Only thing is the Ampere's law is done. The sixth shape is toroid. There is nothing there. Toroid is just a result. We don't even have any problems on that. So next class when we catch up, we will do more of that. Maybe if time permits, maybe we'll do a little introduction about EMI also. Okay, with that we'll wrap up for the day and do start solving. Right? Don't wait till long. Try to finish off magnetic field and force, I think, by at least next Friday. Okay, with that we'll wrap up for the day. So any doubts in the class notes, anything, please stay back or else you're free to leave. I'll see you on Friday, same time. So take care, stay safe.